So hello everyone. I'm going to talk today about P2P on the web. Apologies if I seem a little out of it. It's because I am. So let's talk a little bit about the promise of the internet. The part that we have done is we've built a universal application runtime with HTML and JavaScript and CSS and WebGL and Webrtc and all of this really great technology. But the best part is that anyone can just throw up a web page, although you have to get an SSL cert for some of this stuff now, but that's free, I guess. But these promises are sort of not living up exactly to their expectations. This is particularly obvious if you go out to an area where you do not have good internet. Like back in April, I was in Guyana for 2 weeks, and we had the maximum time on a ping that I saw was 31 seconds. And I think I loaded several web pages over that satellite connection. So that was a great learning experience. Also, a lot of these services that we depend on every day, who knows how long those things are going to be around? GeoCities shut down. That was pretty great. I had 2 GeoCities pages, and it was the best. You could get into web development. It was fantastic. Also, these days there's NeoCities, and the people behind that are working on this problem. They're very aware of it, so I'm really glad to see that. Also, one really kind of bad thing about our web is that we seem to fetch the same exact pieces of information over and over again. And my computer has plenty of space, so why can't I just save a map of a city that I've looked at? It's a megabyte or 2, maybe. Why do we have to go to Google Maps every single time and fetch tiles that we've fetched over and over again? Cities don't really change that fast. And of course, as was very nicely put in the last talk, the cloud is just somebody else's computer. So when we build systems that depend on HTTP, on servers, we're reducing the resiliency of the systems that we make, because if that computer shuts down, if that domain name expires, if that SSL cert goes all expiry, whatever, I don't know, whatever they do, it's happened to me several times, then our stuff won't work anymore, and that's kind of sad. So here's a really great example to get you thinking maybe about how strange this is. So we both have computers, you and I. I want to send you a file on my computer. So how do I do that? Well, I could send you an email, but when I send you an email, I'm not really sending you an email. I'm copying the file from my computer to my email server, and then my email server is copying a file to your email server, and then your email server is copying the file to your computer, which is a bit roundabout, and all of those hops are just another thing that can fail. I could use something like Dropbox, where there's maybe fewer servers involved, but the problem still remains. If Dropbox goes out of business, then what about all your files? You might like to have those back. This is another really strange thing. If I'm here on this conference Wi-Fi, here in Romania, and I want to send you a file, we shouldn't have to go to servers all the way across the world in California or Virginia or Hawaii, who knows where those servers live, and then all the way back just to do that. That seems very strange to me. So this is going to be a much bigger problem in the future if we extrapolate the size of human civilization, like Mars or moons of Jupiter, places like that, right? We can't continue to send packets all the way back to Earth and back just to send a file a few meters on the ground. So so I already mentioned this, but Google Maps has this problem extremely bad. Also, when you're traveling, that's the time when you most need a map. And that's also the time when you're least likely to have a good data plan. And that's the time when Google Maps will just load incredibly slowly or not at all. Also, for a more concrete example that'll feed into something that I've got in a moment, Google Calendar. So here's my Google Calendar. I just did some quick back of the envelope file save as math here, and it downloads over 3 megabytes, over 3 megabytes just to view a calendar. And if I'm downloading that over a poor 2G connection, that's kind of pretty heavy to download what might be a kilobyte of text, a very, very small amount of data, and we're sending these gigantic payloads. And we have this universal application runtime with all of these really great features like IndexedDB, like app cache, like service workers, but we're not using any of that right now. And it's very strange to me. Why? Because GeoCities, never forget that. This has happened before, this will continue to happen. I find that whenever I use these kinds of services like YouTube and SoundCloud, I'm just counting down the time before it will unceremoniously be shut down and put into a box somewhere. I think that's perhaps a useful mindset for building this kind of stuff. So peer-to-peer is a way that we can make the web great again. Here's the future that I want to live in. If I have some files and you have some files, we should use our computers. Those computers might be a phone or a watch or a smart thing in a home, whatever. We should be able to copy those through the network that is already there without going all the way out halfway around the planet. That seems somewhat obvious, but we don't really do things that way very much. Also, reliable internet connections are a really big luxury that you only have in certain circumstances, certain economic backgrounds, certain places on the planet. And the planet is really big. And there's more than just this planet. There's asteroids and Mars and L2 points, all kinds of fun places where we might want to use technology. And we shouldn't have to load 3 megabytes every time we want to pull up our calendar on the asteroid belt. So here's a way that we can do this. We can build services that nobody can own, because if nobody can own these services, then nobody can shut them down, not even you, and your own worst enemy is just future you. I learned this great lesson from Dominic Tarr. I think it's a fantastic way of putting it. But if we can design these systems so that not even we can ruin them, then I think maybe we'll have a chance at building something really great. Here's some more reasons why your worst enemy could mess up your service. You could get bored. You could turn really evil and go work at the NSA. You might sell your service and then it will just get shut down, or who knows what will happen. And I think we really owe it to the people who use our technology to make it so that they're not constantly dependent on us for how they use those tools. Like people who make hammers don't have this relationship. People who make other kinds of tools don't have these kind of hierarchical relationships with the tools that they make. So I don't think that we developers should either, if we can design something better. A nice side benefit of a lot of these techniques is that they scale forever. In fact, they scale the opposite way of a hosted service, because the more people use your service, the better the service will work for everyone. This is especially true in the case of BitTorrent, for example, where the more people are downloading a file, the more people are also serving that same file to everyone else. So everybody wins if we build systems like this. Unfortunately, when you build a system like this, congratulations, you're building a distributed system. It's very difficult. So I'm going to try to help you out with that with some small modules that I think are really fantastic and really underused that we can use to make things that implement these peer-to-peer ideas. I'm especially going to be talking about hyperlog in this talk. So hyperlog is an append-only log. It's an extremely boring data structure. It's literally, it's just a log. You write things to it. You can only write new things at the end. That's what makes it append-only. And you can read it, of course, but you can't modify it. So the nice thing about a log, especially a log that is this thing called a merkle DAG, just like Git, is if each document can point at the hash of its predecessors, then you get all of these really great properties. Like for one thing, the graph, you can get that graph from third parties who you might not even trust, and you can verify for yourself that the graph that you've been given is accurate. So that means you don't have to trust who you're getting the data from if you can establish a side channel, just a small piece of information to establish the veracity of that data beforehand. So we can start to use the capacity of the network, the capacity of our peers to build capacity, to build infrastructure. Also, replication is extremely trivial with log-based structures. I mean, if you had a very, very simple structure, you might even be able to do this with the cat command, where you just literally concatenate two files to generate the new file. And then you can build some really great stuff. So I'm just going to quickly go through a demo here about how you can use hyperlog. So make a file log.js. I'll require hyperlog, like so. Hyperlog requires a level DB handle. So in Node, you can require level. In the browser, you can require level-browserify, which we'll be doing in a bit. So you give level DB a place like this, whatever.db, or I think I've used that one. I'm going to make up a different name so that my demo doesn't destroy itself. And now we can make a log by calling hyperlog db. And it's also really nice to pass in a value encoding of JSON. You don't have to do that, of course. So now we've got a log. What can we do? We can call a few methods. We can call log.add, log.append. Log.add takes that list of predecessors as the first argument. I don't know how to spell predecessors. Log.append will add that information for us automatically, though, for the node that we know about locally. That's the most recent. So I'm going to use log.append. But first, I'm going to check if process argv2 is add. If it is, then I'll append a little document. I'll get a message from process argv3. And that's it. Now let's make a list command. So we can do process.argv2 is ls. We can log.create read stream. And you can filter that a little bit if you want to, but I'm just going to print it out to standard out just to show you the basics. So we run log, add, beep, boop, and we run log, add, hello. And now we run log ls, and there's our data. So you can see that each document, this key is the hash of the contents. The hash of all of this contents, including the links, and that's kind of important to establish a Merkle structure. And here we go. In the second document, we're pointing at an array of links, and there's one element in that array, and it's the hash of the previous document. We can model other kinds of advanced use cases by doing things like, just like in Git, when you have two forks that have, because of concurrent edits, you can merge those two forks back together by giving both hashes to that links array, not just a single hash. So we can use hyperlog to implement this great architecture for peer-to-peer systems, and actually for data centers as well, because data centers are also distributed systems. It's called the Kappa Architecture, and the basic idea is that you have an append-only log that serves as a source of truth. So you append things. You're basically accumulating observations or accumulating facts about the world, whatever they may be. And then you build these indexes called materialized views. But the indexes only contain derived data from the log. So the log is the complete arbiter. It's the final say in how your system works. And everything else is derived from that. So you can imagine you can use these materialized views to speed up things like answering particular kinds of queries that you otherwise might have to read every single document in the log every time you needed an answer. So it's a simple caching scheme. But what's really great is with that simple caching scheme, if you've ever done a migration on a mutable database, you might understand the pain of how difficult that can be. But with this architecture, if you're using something like LevelDB, you can literally delete the index database directory, and these materialized views can just be regenerated from the log. So long as the log doesn't change, it's a very powerful, very great way to evolve a system over time, I think. So here's what that looks like with this module called hyperlog index that I've been working on. You pass in the log. It's the hyperlog object. You pass in DB. This is like a level DB handle for some bookkeeping that this module needs to do. And you pass in a map. And your map, it can store data however it wants. So you can write to You can write to an SQL database, you could write to a flat file, you could write to LevelDB, whatever you want. But the important thing is that your function gets called for every document in the log in order, and you should call next when you want the counter to advance. And then when you perform queries, you can call dex.ready to check to see if the log is completely up to date yet. So you can buffer your querying based on when your log is completely ready. So I've built a key value store on this that we're using in some very remote places for some projects I've been working on. It's called HyperKV, and it builds one of these materialized views that give you a key value store. But the catch is that because these hyperlogs, they're built for a distributed system, they're built for a peer-to-peer system, so there's no single source of truth. So if two people are editing the same key concurrently, and they go to merge their data, the only true thing that we can say is that, well, there are two valid versions of that key, so we should represent both of them. And I think that's just it's going to be an interesting interface challenge for systems that are built this way, how to best represent the truth, which is that there are multiple pieces of data, instead of hiding it or trying to figure out something automatically, because people have done that and it hasn't really played out very well. So let's look at HyperKV. So I'm just going to make a quick demo. This is going to be the last exact demo, so I can copy our log from before, and I'll call this kv.js now. So we can require HyperKV, like so. And then we set up our KV after we set up our log. So we do HyperKV, pass in the log, pass in a dummy database that we'll need for some stuff. So kv whatever.db. It's definitely not going to exist. We can pass in a map function if we want. Oh, no, this is HyperKV, not hyperlog index, so we don't pass in a map function. HyperKV takes care of it. Now what we can do is, instead of add and ls, we can have some other things like put and get. So let's make a put. Instead of calling log.append, HyperKV can do that for us now. And we can call kv.put. We can get the key from process arg3, and we can put a value. Maybe we'll just keep that basic structure with the messages. That's kind of nice. Or I'll just do that. Actually, this should be a different value as well. OK, that definitely doesn't exist. OK, so then you get a callback if you care. I like to care during talks so that I know why they're not working. Now we can call kv.get on process argv3, and we'll get values, plural, not single value. And I'll just print out what it is. OK, so if I run this program, I should see the values in my KV store. So if I run kv.js, put message hello, put message, well, now I can get that key, get message. I should get back the string hello, and I do. Oh, whoops, I get the string message, whatever. That's good enough. I can put another string, whatever. I think I messed up the arguments, but that's OK. Anyways, you get the idea that you can do puts and gets, and it all should work out. So I've used these basic primitives, hyperlog and hyperkv, and also this other thing that I won't go into, except that suffice it to say I read a lot of academic research papers before implementing this part. It's a spatial index that works in Node in the browser. So I've got a nice sequence for that. If I go into this directory. So let's build let's instantiate a peer-to-peer map database anyways. We're not going to build one exactly. So you give OSM P2P a directory for it to store its files. In the browser, it'll just use IndexedDB if it's available. We can have a create function that'll take a document like this. So that's behind the scenes calling hyperkv's .put method, and it's doing some other things with the spatial index. We can also have a query function, and that's querying that hyperlog KDB index that is also a hyperlog index. So if we do these things, we can also have a sync function this just concatenates the log structure with another log, if you have one. So I'm using standard in and standard out for that. And that's basically it. So now we can use this map data. So here I've prepared some inputs. So if I run that command, I can create one document. I get back the ID. I can create another document with some different coordinates, perhaps, like that. I can make a third document with yet more coordinates. Now I can finally query the map data by just doing query, and then I give it like 61 degrees north to 65, and negative 148 degrees to negative 145. So I should get back, yeah, I get back some data from my database, and everything looks like it's working well. So the nice thing about making that replication system so simple is that we can use all kinds of different methods to perform replication in real-world contexts, because who knows what kinds of places our technology will be used. For this project I've been working on, the main method of data transfer is USB drives, because there's no internet, there's very little cell phone coverage, and USB drives work very well for that kind of problem. But in other circumstances, you might want to use Bluetooth, you might want to use a local Wi-Fi network if you have one, maybe even QR codes. That would be kind of cool. So here is that map database. So this is a peer-to-peer map database. You can edit it. It's using ID editor for the edits. You can save things. But the coolest part is that when you click this button, which is synchronize, then it prompts you to select your USB drive, and then you take your USB drive, you plug it into your computer, it'll do the synchronization, you take your USB drive out of your computer, you hop on a quad bike to the next village, it might be 4 hours by quad bike away, you plug it in their computer, you bring it back, and now both computers are set up with exactly the same state of the database. So I think that's a really fun project that I've been working on. I'm going to play a little clip. This was on Al Jazeera, actually. It was in Al Jazeera on May 20th, and that's the application that I've been working on with this database. I thought that was pretty great to see on TV. So what other kinds of things can we build? I think this is a really great use case. I've been wanting this to exist for about 2 years. So finally, just about there, let's make a peer-to-peer calendar, because that Google Maps thing, it's a bit much to download. So we're going to need a few pieces for that. We'll need a schedule parser, kind of a calendar database to hold that data and to perform queries based on different ranges of dates. And we'll want to put that calendar database into a hyperlog index so that when we write records to our hyperlog, our calendar database will be updated automatically. So here's some modules you can use for that. I've written them. One's called parse messy schedule. Another is calendar DB, and then of course there's hyperlog calendar DB that provide all of these things. We're also going to need this command. This is called dupsh, and it just runs 2 programs. It takes the standard out of the first program, pipes it into the standard in of the second, and vice versa. So the standard out of the second is piped into the standard in of the first. So what can you do with that? Well, we can do peer-to-peer replication, which I'll show you in a moment. It's a great way to test out these kinds of symmetric protocols for peer-to-peer systems. We'll also be using this command. It's like netcat, but for WebSockets. So it works, if you're familiar with netcat, you can create a little server very easily. You can also create a client very easily. It speaks standard in and standard out on the command line. So I have prepared a little sequence to show you this. Let's build a peer-to-peer calendar. Okay, so first we're going to need some modules. Those are the ones that I was showing you about. The calendar index, hyperlog, of course. We're going to be using an arguments parser, because that's a very thing to have. Now we can make a hyperlog, and when I pass in -d or --datadir, I can give the database a different place on the file system to store data, and that's going to be handy for making some separate databases so we can do replication between them. Okay, So the next thing that I can do is instantiate the index with some parameters, and I can make an add command. Here in the add command, I'll write to the hyperlog directly with a time string. You'll see in a moment how that works. And I'll have a sync command as well. This uses standard in and standard out to sync, and we can use dupsh to wire it all together. Okay, the last part is if I don't get an argument that I know what to do with, I'll just print out the current month. There's actually a bug in this, so this prints out the previous month, but you'll get the idea. When we make that query with these range iterators greater than and less than for dates, what we can do is pipe those results which are streaming to standard out. So this is just some pretty printing for the key and the time string and the title. Okay, so that's it. It's our peer-to-peer calendar. Let's use it. Here's the whole thing, if you want to see. It's very, very small. So, if I run cal.js with -da, temp a, I can run add, and I can give it a string, like every Thursday, we're going to have an event called JavaScript Study Group. Actually, every Thursday at 7 p.m., to be more precise. Meanwhile, I'm going to edit a second database that's going to be stored at /temp/b. And this is going to be every Tuesday, maybe at 8 p.m., and that's going to be called Hardware Hack Night. Incidentally, these are real events that I always use as examples at my hackerspace in California. So here we go. So now if I run node cal.js on one of those databases, I see one result set. If I run it on the second database, I see the other result set. So now let's try to squash those together. So we're going to use the sync command. I'm going to run the dupsh command with node cal.js, temp a, and call sync. And then we're going to run a second version of cal.js with temp b, also run with sync. So it doesn't always end when it's finished, but if I do Control-C, then it usually works. So take a look. And indeed, we have both of the events in our peer-to-peer calendar. So that's all that it takes. So let's do the same thing in the browser. That'll be fun. So I have an example that right here. Oh yeah, it's already running in this part. So, oh, actually, I should show you how it's built, because I put in the effort already. So now, instead of level, you require level browserify. Same modules, though, calendar index and hyperlog. We can make the hyperlog instance, and we can make the calendar database instance. We can use some simple front-end modules that I like to use and wire up a little front end. This is going to have a form with 2 input boxes. One is the time and one is the title. And when we click that form, it's going to append into our hyperlog. Then when you've appended into the form, it regenerates the list, which I'll show you in a moment. So this just renders out the text in a similar way to how we were doing that on standard out. And finally, I have a sync form. And when you click the sync form, it uses a WebSocket module to pipe the replication into that WebSocket and vice versa. Finally, we have a list command. This just does the cal.query like we were doing before and updates the results. So that's all that we need to do for this peer-to-peer calendar in the browser demo. So this is the whole thing. A little bit bigger, but 72 lines. That's not so bad. So here I have it running on localhost 8000. I'll make it a little bit bigger. So what I can do, I could add an event. I kind of don't want to test that, though, because I would rather do this first. So we can use this WebSocket part first to replicate with our existing data set that we just made on the command line. So I can go back to the cal directory, and I can run node cal.js -d temp a sync, and I'll run that with dupsh. For the other process, though, instead of another version of cal.js, I can use WSNC to set up a WebSocket server. So this will listen on port 5005. If I click this button now, here's hoping. See if we get any weird errors. Okay, connection closed. Sometimes I still get the data. Oh, address in use. Very good. So that's a different port. Maybe now it'll work. Yes. So we just did peer-to-peer replication in the browser. That wasn't that hard. Your results may vary. So that's all well and good, but we're still using servers. So how can we make this demo even better? Well, we can use Webrtc. And we can get rid of most of the servers. There's still one server. Well, there's two servers. One is serving the HTML. It's possible to get around that, but it's a little bit tricky. The other one is just a signaling server for Webrtc. So that's just a server that doesn't do very much. A handful of them can probably service the whole internet, so that's not such a bad problem. It'll be good to figure out different ways of doing it, but that's what we have to work with now. So I have another sequence for that. It's very short. So we're going to modify our existing code that I just showed you to use Webrtc. So there's this great module that I like to use all over the place called WebSockets. Or sorry, that's what it was before. I also use that module all the time, but that's not what I was going to show you. So we get a peer event. This peer is a stream, so we can pipe that data connection through our replication, just like we've done a few times before. So, moment of truth. Here's the whole code base now. It's also quite short. Let's see if it works. So here I've got one version. I can run a second version now. If I run on, actually, if I run on localhost 8000, I should have that database already there. Sweet. But that's speaking WebSockets. Hang on. Let's just make some new events. That'll be good. Oh, yeah. Ah. Okay. Here we go. Bit of finagling, but here we are. So these have separate databases. If you have an incognito window in Chrome and a non-incognito window, they do not share the same level DB, or they do not share the same index DB, I should say. So I'll just make the same data that I had before because I'm not feeling very imaginative. Every Thursday at 7 p.m., title, JavaScript study group, add. Now I'll run sync. And over here, I'll run sync as well. Sometimes takes a moment. And there we go. I just replicated over Webrtc without going through any servers. So to recap a little bit, here's what we just put together. We wrote our calendar documents to this append-only log. The calendar database is generated completely from the log, so the log is the source of truth, and our calendar database is a materialized view that indexes that log. We run queries on the calendar database, so that's the cal.query code that I was showing you, and we replicate just by a simple, not exactly so simple, but it's simple in concept, by concatenating those logs together. That's all I have. Thank you very much.